Nuclear reactions, I guess part 2, because we did decay in class. And now we just need to talk about the other ones, and I'll go as fast as I can, but you know me. All right, so different types of nuclear reactions. We talked about nuclear decay, which was all about the instability of the nucleus, and it just happens, like the nucleus is unstable. The other ones we need to talk about, and we will go in order, are transmutation and bombardment. So we're going to talk about that one first. And this is the kind of nuclear reaction, unlike nuclear decay, which is just completely natural in the sense that it just happens. There's nothing that you do to it. This is the kind of nuclear reaction, that occurs, okay, I'm unable to write, it occurs in particle accelerators. Particle accelerators use magnets in order to get two atomic nuclei to go very fast at each other. And essentially, this is how they make new elements. Specifically, this is how they make the transuranium elements. Because uranium is the last naturally existing element, which is atomic number 92. And if you look at the periodic table, there's certainly more elements than atomic number 92, but all the rest are man-made. So if you grab your periodic table, take a look. I mean, there's plenty of them that have been man-made through the periodic table. Plutonium, for example, which is found in weapons. Americium, which is found in smoke detectors. There's actually a radioactive source in smoke detectors that if the little beam of radiation is interrupted by smoke, it will cause an electric current to occur, and that's how your smoke detector works. And then there's plenty of others that have been made, for fun. They don't have any uses. We used curium, could be an example. Anything past atomic number 92. But the main idea here for this is that if you take, for example, an alpha particle, and you shoot it at something else, say boron. And in a particle accelerator, they use magnets and miles, and they get these things going very, very fast. So they literally, the two nuclei hit each other. Think target practice. This is not something that happens easily. Nuclei are very, very small. But if that happens, you can end up getting those two nuclei to fuse together and produce something larger. Like in this case, nitrogen 13. Although if you take a look, that doesn't add up, so we're going to have to add a neutron. That often happens, that neutrons are given off and they don't combine perfectly, so this is given off. Now my question to you is this radioactive? And you should be able to answer that correctly. And of course the important question would be why that is radioactive. Think neutron to proton ratio. Okay, so that's the first type, and again, we're just going to breeze through these fairly quickly, so we don't need to say a lot about that. But that's bombardment. Notice this is not a huge one like the transuraniums, and then the transuraniums, they might take two small atoms in these places and try to get them going very fast in a particle accelerator and blast them together and hope they stick. That's the idea, and that's how they make all those transuranium elements. Third type, fission, which is extremely important because it's what fuels our nuclear reactors. It's part of what makes atomic bombs. Well, it's the key component to how an atomic bomb works. And the idea in fission is literally that if you take, there are some forms of elements that have unstable nuclei. For example, uranium-235, it's got an atomic number greater than 82. It's unstable, but it just isn't quite able to spit something out of the nucleus, so it just needs a little bump. And that bump can occur in the form of a neutron, that if a neutron hits this, it's so unstable, it literally could break apart into, this breaks into pieces. That's why it's called fission, into two smaller pieces. So it might break apart, for example, into barium and krypton are fairly common results of this, but not the only possible results. And it also will give off some neutrons and some energy. This is an example of a fission reaction. So I'm just going to highlight a couple things. Here's your uranium-235. If a neutron hits it, here's where it could break apart into the krypton and the barium. But the key thing with this is that in addition, it also gives off those 3 neutrons that I put in the equation. Well, if you have additional uranium, it could hit that uranium and it will split it. But what's most important about it is that energy that's given off. So when this one splits, it gives off some energy, which would be in the form of heat. And when this one splits, it gives off energy. And then when these split, like if those neutrons hit more, what we have is a chain reaction, and we have an enormous amount of energy. Now the amount of energy is related to Einstein's equation, E = mc squared. Because it turns out that when this splits into these two and the neutrons, it loses a teeny tiny bit of mass. If you take that mass times the speed of light squared, some energy is given off. And as long as, if there's a lot of uranium present, in other words, a critical mass is the mass required for an uncontrolled chain reaction to occur. So if there's more and more uranium, if there's lots of uranium, then those neutrons will continue to hit it and produce more energy, and it will explode. That's the concept of an atomic bomb. In the atomic bomb, you actually take a critical mass worth of uranium and you divide it into 2 pieces. And so if you take your 2 pieces and you separate them, but then upon impact they come together and they create a critical mass, it will be an uncontrolled chain reaction and the whole thing will explode. It's also the basic idea behind a nuclear power plant. So let's pull this up. If you take a look at a nuclear power plant, and you guys I'm sure have learned this before, but in this is just a general picture of a nuclear power plant. We've got the reactor. These black things is what's known as the nuclear core. These are the nuclear, these are typically made out of uranium-235, which is fissionable, but there's not a critical mass worth of them, even though they're divided into all of these. But what happens is they divide it up, and these control rods will move up or down. When they move down, they separate all of these uranium pieces from each other, and there's basically no fission reaction. When they move up, a fission reaction starts and neutrons are given off and it bumps into stuff and it produces energy. Well, that energy is used to heat water, which is found here. The water circulates around and then gets heated up again. There's a secondary part, which is this purple area. This hot water, it's superheated, actually it's under pressure, is used to heat this water up, which turns to steam, which runs a turbine, so we get electricity, and then gets here, and then there's a tertiary or a third system where this is a lake, for example. Its sole purpose is to cool this water down, so it goes back to liquid water and around again. So that's the premise of our nuclear power plants. Of course, the core, which, let's go back to my page. Maybe it's this, yes. What happens to the core itself in a nuclear power plant or in a nuclear bomb is it produces these, which are the products. This is essentially what is in nuclear waste, that people are rightfully concerned about, because these are radioactive as well. So there is an issue with that, and certainly there's more information in your book on that as well. And then the last one, fusion, which is what occurs on the sun or in the hydrogen bomb, which is different than the atomic bomb. But with fusion, essentially what you do is, and this is one possibility of fusion, but if you could get two nuclei to combine, again, perhaps in a particle accelerator, but our luck with that is not good, so it needs to be faster than a particle accelerator. But if you can get them going so that they hit each other and literally fuse together, not break off any other pieces, but fuse together. In this case, for example, you could make helium. Now, this is not an alpha particle, this is a helium atom. Turns out that when you add up the 2 protons and the 2 neutrons, and then you add up the mass of the helium, turns out some mass is lost. And so, Einstein is right again, that small amount of mass that gets lost is converted to large amounts of energy, and so we get an enormous amount of energy out of this. But this is not radioactive. And so this would be a wonderful way, if they could ever figure it out, to use a nuclear power plant, because there's no nuclear byproducts. But the trouble is that it takes so much energy to get this to happen, and the amount of energy we get out of it, that it's too difficult to get to that high of a temperature in order to cause it to happen, and then the amount of energy we get out is difficult to harness. Happens on the sun all the time because of the high temperatures on the sun, and this is what fuels the sun, this energy. In a hydrogen bomb, what a hydrogen bomb actually uses is it has a fission reaction which produces an enormous amount of energy, and that fission reaction's energy is then used to fuel a fusion reaction. And so a hydrogen bomb is just that much more destructive, because you get all the energy from the fission reaction, it fuels the fusion reaction, which gives even more energy, and then it's an extraordinarily destructive weapon. All right, so that finishes up our types of reactions, and then we will move on and chat about more tomorrow.